Weather is, we're going to talk about a lot in weather. Weather is one of the biggest sections uh, that we're going to cover. Basically, we're going to go from the ground up. We're going to talk about weather theory. We're going to talk about uh, how weather works, different fronts, clouds, I mean, everything. We'll go into pretty significant detail. The FAA really wants you to have a good understanding of how weather works because we're flying through it. So this is one of the the bigger sections that the FAA pushes. Um, so yeah. So first off, why is weather important? Well, weather's important because, well, we fly through it. So we're in the atmosphere. We're in this constant changing environment around us, and we need to know how to interpret it and how to predict what's going to happen. Because in reality, most pilots should not rely on the weathermen on TV, because those people, although they might be right, um, sometimes don't deliver the information that you need, especially when you're flying across the country from one place to another. Weather changes very rapidly. You need to know how the weather is affected on a larger scope in order to navigate that safely. Um, so some of the topics that we're going to be covering is going to include basic weather theory, so things like pressure and atmosphere and instability and all kinds of fun stuff, to clouds. So we're going to talk about different types of clouds and how they form. We're talking about different weather products. So these are places that you can go and see different types of weather data. So whether it be aviationweather.gov or the NWS site or NOAA or some other federally reputable sources. We'll talk about where you can go and get some of this information. And we'll also talk about some regulations that surround some of these weather things. So first, let's start by talking about the atmosphere. So the atmosphere, as you probably know, is made up of mostly nitrogen gas, about 80% nitrogen gas. The rest of it is made up of oxygen, and then trace amounts of argon, carbon dioxide, particles like sand and dust and other things. And so with that concentration and makeup, the atmosphere is further subdivided into different layers, extending all the way out into basically nothing. So the base layer, the troposphere, is the bottom layer where we live, and it's basically where all weather happens. Not a lot of weather happens above the troposphere. The troposphere is where the air is the most dense, and it occurs where the surface is to wherever about 4 to 12 miles up, depending on what the terrain looks like and other atmospheric conditions of that time period. So the troposphere is, uh, like I said, where most of the weather takes place. And inside of it, the troposphere has what's called a standard lapse rate. Now, the standard lapse rate is going to come up a lot, and it's one of the basic fundamentals of weather theory. And basically, what it says is that as you go up in height, temperature decreases. Now, there are exceptions to this rule, which we'll talk about, but what you should know is that as we go up in altitude, every 1,000 feet, temperature decreases by 2 degrees Celsius. And similarly, the pressure also decreases as we go up, which that decreases by 1 inch per 1,000 feet. So if you can know those two numbers, that's a good starting point to why a lot of weather happens. And because most weather happens in the troposphere, these lapse rates really apply in the troposphere, and this is basically the only weather layer we're going to talk about. The other ones you can go look up more later, but they're not very applicable to what we're doing. So troposphere does have another layer above what's called the tropopause, but not much happens in that layer. I'll just know that the troposphere is where we live, where everything happens for the most part. So the tropopause does sometimes have unique weather features such as clear air turbulence, depending on what its altitude is and other weather conditions. That's things like little eddies that form, and you can't see them because there's no features around them. usually this is encountered by jet airline pilots, but we'll talk more about that later. So another basic weather theory here is what's called atmospheric circulation. So inside the Earth's atmosphere, Earth is split into different kind of cells and zones, and these zones operate differently from each other, mostly in the way that the air is moving in them. So in different bands across the Earth, as you can see in the top right picture here, we see the prevailing winds move in different directions. In fact, they kind of swap directions every band as we go up, and these different cells make up the weather pattern. This is why in North America, where we live, all of the storm systems move from west to east, and then if you go down to the south into the Gulf, all the storms move from east to west. This atmospheric circulation is due to different factors, some from the heating of the Earth's surface to the fact that as warm air rises, and as it rises, it cools down, and then it sinks. This causes air to circulate. The Coriolis effect plays a large role in this as well. That's what causes the different arcing patterns of prevailing winds. And of course, matter of fact is that air is much cooler at the poles than it is at the equator. And so we kind of get this motion moving from the equator up towards the poles and then back down and circulates. The Earth also has a tendency to rotate off axis, which heats the Earth at different temperatures depending on the season. So in the summer it's hotter, in the winter it's cooler, and this causes different cells to form and unequal heating, which causes air to circulate. The atmosphere also has pressure, which I'm sure you've heard about, and like we mentioned before, the pressure decreases by 1 inch per 1,000 feet. The atmosphere is measured in inches of mercury. However, there's other measurements of pressure. Just use your standard unit there. We're mostly going to be talking about inches of mercury. There's also millibars, but we'll talk about what that means later. Atmospheric pressure is measured, at least theoretically, by how mercury is, how much mercury is in a tube given a certain amount of pressure on it. So in this picture you can see that you have a base with some mercury in it, and as the pressure increases or decreases, the mercury can move up into this tube and move up and down. And this is how pressure is measured. This is why it's called inches of mercury. It can be measured other ways, but this is kind of the base of how pressure was measured, at least in the early days. This pressure moving up and down is what we refer to as different types of pressure. So high and low pressure, which we'll talk about later. And this can cause different types of weather patterns and flowing of air currents and such. But the major thing that you need to know from here is that the standard pressure is 29.92 inches of mercury. And the standard pressure is what we kind of define as like normal, the baseline. So sea level is at 29.92 inches of mercury. And specifically, we say that it's standard at 15 degrees Celsius. So knowing those two measurements right there is going to get you a long way, the standard pressure and the standard temperature. And everything above standard pressure is considered to be a high pressure, and everything below is considered to be a low pressure. And this can affect flight performance. So in a high pressure scenario, it's going to take a lot longer to take off than it would in a low pressure scenario. And we can see this if you watch videos of airplanes taking off in high altitudes like Denver, where they're almost a mile high, and you can watch videos of people taking off in like near the ocean and stuff. The amount of runway that they need is a lot less down low than it is up high because of aircraft performance. And aircraft performance in much denser air is a lot better for various reasons, which we'll talk more about in aircraft performance section. But just know that higher pressure is affecting on the aircraft performance. Altitude and pressure also affect human performance. So this kind of gets into human factors a little bit, but since pressure decreases with increase in altitude, the air density also decreases. And what that means is that there's less oxygen for us to breathe the higher we go up. The FAA has put certain regulations out, in fact, to determine when you need to put on supplemental oxygen in order to be safe. So the base guideline here is that basically hypoxia can happen as low as 5,000 feet at night. And hypoxia is the condition that occurs when you have a lack of oxygen. And hypoxia can lead to a lot of different complications. And so to avoid this, the FAA put into effect regulations which say that basically at 10,000 feet, you need to start thinking about putting on oxygen. Now, the actual regulation says that I believe it's 14.5 or I think it's 14,500 feet. You're required to put on supplemental oxygen, but between 10 and 18,000 feet, you could have no oxygen. We'll get more into this with the FARs, but just know that because of the lack of oxygen up at these higher altitudes, hypoxia can set in, and this can cause various problems for the cabin crew and the pilots. So wind patterns are formed by various things. High and low pressure plays a big part in it. Now, like we were saying earlier with standard pressure, at 29.92 inches of mercury, everything above standard pressure is considered high pressure, and everything below it's considered low pressure. And this affects the way that the air moves. So in a high pressure scenario, this is air that is moving in an anticyclonic motion. So let's say we have a pressure of 30.0 inches of mercury. This means that the air is going to try and move to an area of low pressure to try and equalize. And the way it does this, at least in the northern hemisphere, is it moves clockwise and outward from the high pressure because of the Coriolis effect, and it moves towards an area of low pressure. Likewise, an area of low pressure is an area of ascending air, and it's moving inward towards itself, and it's moving counterclockwise. Now, low pressure systems are most famously noticeable in hurricanes, where you can see them coming up the coast, and they always rotate counterclockwise in the northern hemisphere. And those are severe areas of low pressure, sometimes as low as like 960 millibars or even lower. So high pressure is almost always associated with good weather. It's usually drier. It's just nice. So if you see a high pressure on a weather chart, you know that the weather's probably going to be good. Low pressure, likewise, like I said, with the hurricanes, is usually brings bad weather. It's drawing in a lot of wet surrounding air. It's kind of like a collection point. And so low pressure systems are always associated mostly with bad weather, clouds, thunderstorms, you name it, hurricanes. So knowing that the high pressure and low pressure is bad weather, high pressure is good weather, is basically all you need to know right now. The other thing that's kind of interesting to think about is that if you're flying flying against like the grain, I guess you could say, of these pressure systems is going to be a lot harder than it is to go with it. So in this case, in this picture, you're seeing if you're flying from the top right corner down to the bottom left corner, you'd be flying with the wind of the high and low pressure as it moved towards from the high to the low pressure. You'd be flying with it. Now, if you went the other way and tried to fly against that moving air, it'd be a lot harder. And this kind of brings up the idea of flying with tailwinds if you can. So when you're flying and planning long cross-country routes, it's good to think about where these high and low pressures are so you can kind of find a fast route if you're flying as a private pilot at least. The next thing that we're going to talk about is convective currents. So convective currents are basically due to different heating of the Earth's surface. So different parts of the Earth heat at different rates, and this causes currents to form where warm air is trying to move to cooler air. Now, these are much smaller scale than the large scale air mass movements of like air moving from the equator to the North Pole or something. But these happen on a much smaller scale, and they cause much more drastic weather patterns than or weather phenomenon than those larger ones do. So convective currents, they can cause turbulent air, they can cause eddies, they can cause land and sea breezes, they can cause unstable approaches if you're not careful. And we'll kind of talk about these as we go through some pictures trying to depict what we're talking about here. So in this picture, you can see a depiction of a land and a sea breeze. Now, this type of convective current happens depending on which way it's going, depends on what it's called. So a land breeze is when the sun heats up warm or heats up the land faster than it can heat up the water. And what that does is it causes warm air to rise, move over towards the cool water, and then it drops. And as it drops, it comes back and moves towards the land to be heated up again. And this causes a sea breeze. I think I said land breeze. I meant sea breeze. So this causes a sea breeze to form. And you can notice this, especially if you're near the lake on a hot day when the water's kind of cool and there's a strong breeze coming off the water. Well, this is due to the fact that the land heats up faster than the water does. And it causes this kind of convective current to form where it draws air back onto the land. And the same thing happens at night when the sun goes away. The land starts to cool faster than the water. And so the water heats up the air and it moves back over the land and descends and it moves back out towards the water. Some other types of convective currents happen like over parking lots or large sections of towns where there's a large amount of asphalt or concrete or other surfaces that heat up differently than the earth does. And so what that does is it causes air to form a pocket of faster rising air than otherwise would be. And it can cause little bumps in your flight path, and it can cause turbulence. And this can cause problems mostly when you're trying to land. And like in this picture, you fly over a parking lot, it bumps you up, and then you fly over a lake, which is cooler and it's sinking air and pushes you down, and pretty soon you're off your flight path. So these are just things to think about as you're flying, that these convective currents exist and that these smaller scale air currents can form. So some of the things that can happen around airports and terrain are ground obstructions to the wind. So as the wind moves across the Earth's surface, it does want to flow in a straight line, and it normally does at higher altitudes. However, on the lower levels near the ground, especially in mountainous terrain or hilly terrain, this wind gets moved around. And all these buildings and trees can affect the wind direction. And in fact, wind can sometimes be up to 90 degrees different from where it is in the ground to up in the air at 6,000 or 8,000 feet. So as the wind moves across the ground, it bumps into buildings and has to move around them. And this causes different air patterns to form. And it can be very unpredictable at times. So like if you're taking off of this runway here in this picture, it has these buildings right here and the wind's moving around it. The wind isn't really moving in one direction, and it can be hard to predict where it's going to go. And so especially if it's a really heavy windy day and you're flying down this runway, it'd be something to consider that these buildings are here and that you might get bumped around and moved in different random directions as you're taking off or even landing. Natural obstructions also can happen to cause this. So mountains, if wind moves up and tries to go around a mountain, it's going to be pushed around on the backside of the downwind side. It's going to cause different random wind patterns to form, different eddies, lots of turbulence, and this can be very dangerous, especially if you're flying in mountainous terrain. You get stuck on the side of a mountain where these currents are happening, they can push you down and you won't be able to climb out, and you'll have to land on the mountain or crash into the mountain because these wind currents are pushing you back towards it. Another type of severe ground wind that is not necessarily caused by buildings or anything but it's called low-level wind shear. Now, low-level wind shear is usually associated more with thunderstorms and strong wind events, so strong jet streams and stuff. But wind shear in of itself is basically just a rapid change in direction and speed of air mass. So at one level, you might have at 1,000 feet, the wind's moving at 30 knots towards the west. And at 2,000 feet, you might have the wind moving at 10 knots towards the east. And that would cause a wind shear layer to form in between those two. And that can be very dangerous. It's most dangerous when it's near the ground, especially when you're landing. And these low-level wind shear events can cause you to lose control, push to the ground, to crash, just because your aircraft, maybe let's say you have a landing speed of 45 knots, like in a Cessna or something, and a low wind shear gust happens and it changes direction and speed up to 50 knots. Well, if you're landing and you're at 50 knots about to land and it goes the other way, and you just lost 50 knots, well, then you're out of airspeed and you're going to crash. And so this is something to keep in mind. And most big airports have a wind shear alert system that will go off and will allow the tower to see if there's been a wind shear event that's happened. They can warn pilots about it. The most severe wind shear event is called microburst, and microbursts happen during a strong downdraft and a thunderstorm, usually a dissipating thunderstorm. When it's kind of disintegrating, will release a lot of wind and it'll all come down at once, and this can cause very severe shift in winds, sometimes up to 90 knots or more. It can break trees and it can do a lot of damage, not just to airplanes, but to the ground as well. They can sometimes be indicated by certain types of weather phenomena, like a rain shaft or blowing dust around the base of it. They could be very wide, up to 2 miles across, to 1,000 feet in height. And like I said, they're very dangerous to aircraft, especially when they're landing. It can cause an insane amount of turbulence. Here's a picture of kind of what a microburst would look like. So you have the strong downdraft in the middle, and as you go into it, it's going to have a strong headwind, and as you go out of it, it's going to have a strong tailwind. So if you're taking off or landing into it, as you go towards it, depending on which way you're going, it's going to have a strong headwind. And then as you're in the middle of it, it's going to push you down. You're going to lose altitude. And then as you kind of get out of it, it's going to start to push you faster and faster. And if you're not careful and don't know what you're doing, or if the wind's just too strong, it'll push you right into the ground. So, all right, so let's talk about how wind is depicted on maps real quick. So wind on weather maps is indicated in different pictographic forms. So here in this picture, you can kind of see when it's calm, it doesn't have any what we call barbs or pennants or anything. It just has two circles. Wind that has a little bit of speed to it and it's not variable, it's going to have this kind of leg coming out, and it's going to have a little barb that's sticking off. And the way you read this is, one, you look at what kind of barb it has. In this case, it's a half a barb. Over in the southwest 20 knots corner here, you can see it has two long bars. This only has a half bar in the northwest 5 knots corner. And that barb indicates the wind direction. So for every half barb, it's 5 knots. Every full barb is 10 knots. And down in the bottom, you can see it has little triangles. Every little triangle or pennant is 50 knots. The long end of this little thing coming off of the circle indicates wind direction. So the wind is always blowing towards the stick. So in this case, the wind is blowing from the northwest at 5 knots. You can see that little stick is pointing towards the northwest, indicating it's coming from the northwest at 5 knots, which is indicated by the half barb. So that's kind of how you read those. If you actually take a look at a real weather chart real quick, let me change my screens. And while we're doing this, we'll also kind of go between weather charts and weather forecast tools. Later, we'll talk about actual forecast tools and how we use them. But for now, I'm just going to go to aviationweather.gov here, and we can actually look at some of these wind depictions on charts. So here I pulled up the map of the UP, and each of these little dots is a weather station. And as you can see, they all have these little weather barbs on them. And let's take Houghton County, for instance. Houghton County has right now a little bit more than westerly wind at 10 knots, indicated by the full barb there. If we take a look at another airport like K.I. Sawyer, you can see that the wind is basically coming directly from the north at 10 knots. And in fact, if we click on it, we can see the wind is coming from 360 at 8 knots. So that's kind of a quick how you read weather charts and how you read wind on weather maps. So we'll kind of go back to our presentation here. Next, we'll look at what pressure looks like on maps. So like we mentioned earlier, with the high and low pressure, highs are always indicated by H's and lows are always indicated with L's. And this is, highs are anything above 29.92 inches of mercury. However, on pressure maps with isobar lines and high and low pressure, it's almost always indicated in millibars. So you might have to do some conversions. Standard pressure in millibars is 1013.2. So anything above 1013.2 is going to be a high pressure. Anything below that's going to be low pressure. And on these pressure maps, they have lines which indicate lines of constant pressure. And these lines of constant pressure will have a marking which indicates what pressure they are. And these lines will kind of be contours, kind of like an elevation chart would have elevations, and these are lines of constant elevation. These are lines of constant pressure. These are good ways to see where areas of wind might be, because certain weather theory says that if isobaric lines are close together, that means that there's a strong gradient, and usually that means that there could be strong winds associated with that. So if you see isobaric lines that are close together, that usually means that there's a strong wind there as the air is trying to change pressures rapidly. Sometimes isobaric lines are nice to try and predict surface winds. However, due to surface friction and stuff, sometimes it's hard, but there are some rules of thumb that say that sometimes the surface winds can be up to 90 degrees off of what these isobaric lines are. So at higher altitudes, at least, wind will flow mostly with isobar lines, but down the ground it could be up to 90 degrees off, so it flows perpendicular to it. It's not always the case, but it's kind of just a rule of thumb. Also depicted on pressure maps are what we call troughs. These are indicated by these kind of dashed orange lines that you see, and there are sometimes ridges depicted. There's none on here, but basically those are areas of extended high pressure, whereas troughs are areas of extended low pressure. And we'll kind of look at one of these charts here. So on the aviationweather.gov site, we can see that this map here has areas of high and low pressure. This is what we call a prognostic chart. And this is the current conditions right now. We can see where these fronts are. We'll talk about fronts later, but we can see these low pressures right now. There's a low pressure off to the northeast of us, and it has a pressure of 10.3. So it's kind of low, but really not enough to cause any significant amount of damage. That's kind of the reason for this drizzly weather we've been having. As this trough moves back over us, it's going to draw some cloudy air and it's going to bring some rain. And so these lines, basically just know that isobars, these gray lines, are lines of constant pressure, and that highs are above 1013.2 and lows are below 1013.2. And you should be good to go as far as pressure maps go. Get back to our presentation here. All right, so I think that we'll stop there for tonight before we get into atmospheric instability. Does anybody have any questions about anything we covered? We kind of went full force into the weather section, but if you have any questions about any of it, I'd be happy to answer them.
Yeah, I do real quick.
Okay.
For those weather map wind indicators, so if that's pointing to the north, that means the wind is coming out of the north?
Yeah, so if this line is pointing north, that means the wind is coming out of the north.
Okay, thank
Yep.
you.
It's a little bit confusing because, it's not really intuitive, but yeah. So just know it, because if you think about it like a windsock, you'd expect it to be the opposite, right?
Right.
So yeah, this isn't representative of a windsock necessarily. So I would, that's kind of something that tripped me up too. So yeah, it means it's coming from that direction.
Okay, thanks for
Yep.
the clarification.
Yep, no problem. Anybody else? If not, I will stop the recording.